Joe.
Can you hear me? Am I mic'd okay? Right in the back? Sounds all right? I'm Joe Justice with Team Wikispeed. I'm an Agile Lean Scrum coach and process guide from Seattle, Washington, the United States. But that's not what I'm here to talk to you about. That's my day job. Nights and weekends, I'm team lead for Team Wikispeed. Wiki is the Hawaiian word for quickly. So Wikipedia would be fastpedia. So Wikispeed is speed, showing you how important we think moving quickly can be. And it's not just moving quickly in automotive space, but it's rapid problem solving for social good. That's what we do. We're all volunteers, and we do night and weekend work. We all have day jobs. And one of our projects, and likely the easiest to use as an example, is our 100 mile per gallon car. Now, 100 miles per gallon in the UK actually doesn't sound as impressive because we measure with different measuring cycles. In the United States, we use the Environmental Protection Agency measuring cycle, which is 100 mile per gallon is enormous. The current generation Prius is right about 60 miles per gallon in the United States. Now, if we translate what the Wikispeed car gets to the UK cycle, we get 158 miles per gallon imperial. That's 1.5 liters per 100 kilometers. We did this using Scrum, and that's what I'm here to talk to you about. But even that's an analogy. What I get to talk about as we discuss building this car using Agile, Lean, and Scrum with this distributed collaborative team, 110 of us in 7 countries. In fact, I believe we're the largest Scrum team currently in operation, at least to my knowledge. Scrum is typically capped at 9 team members. We do it with 110 in real time. But the analogy is, how does this apply to all of your work? How does this apply to all of your day jobs, all of what you do nights and weekends, and all of what you're passionate about? Are some of the advantages Team Wikispeed has found, or at least used, applicable to what you do every day? Our car on the American EPA, Environmental Protection Agency, city cycle achieves 104 miles per gallon. On the highway cycle, 114, and as mentioned, on the UK imperial gallons on its cycle would be 158. Now, that's not a straight conversion, but that's what our simulations tell us it would achieve on the UK cycle, so it's probably close once we do certify the car here. The car is quick. It goes 0 to 60 in 5 seconds. That's similar to a sports car. Not earth-shattering, not supercar challenging, but quite quick and definitely not what you'd expect from an ultra-efficient commuter car. The car weighs just 1,104 pounds. It holds 4 adults, has heating, air conditioning, defrost, a stereo. We're putting an iPad in the dashboard now, so there's some comfort coming our way. It has a top speed of 149 miles per hour. That's plenty enough to go to jail. It has a 5-star crash test equivalency in all directions. That's front, offset front, side impact. When the roll hoops are attached, roof crush, also rear. It has adjustable ground clearance for sport or for off-roading. And it has a cargo capacity that dwarfs most of the cars most of us might have ridden in the last week. It will hold 20 grocery bags or 6 golf club bags. So I'm telling you, Scrum has built this car that's quite sporty, it's ultra efficient, and it's also utilitarian. Well, doesn't that sound too good to be true? Especially when we look at the cars that most of us have been driving lately. This is the Honda Civic Hybrid, a car I'm actually a big fan of. Here it is from 2006 to 2012, and we see that on the EPA United States city and highway combined driving cycles, it's moved up 2 miles per gallon across the last 6 years. And it's a hybrid. Its primary goal is to be ultra-efficient utilitarian transportation. It and reliable. We see that between 2006 and 2009, there were vents added to the bumper, and that's about it. We see that when we go to 2012, the car was restyled, and it did achieve improved fuel economy, but not dramatic, radical change. So how can it be that I'm saying Scrum has built this amazing car, and I'm about to tell you that it was built very, very quickly, that does all these things so well, when the cars that we're used to driving change a little bit year over year, or really every 3 years? It's because manufacturing's tied to the waterfall delivery methodology. Manufacturing and old thought software teams would first gather the requirements. If we were really lucky, they would talk to the customer, but often it was just the board members speaking amongst each other, saying, what is it that we believe the customer would want? It then enters design. Now here's where the cars around us don't change very quickly. The design cycle often takes 10 years, which means that if one of us were to go out and buy a new car right now, it would be the best thing engineers thought that we might want 10 years ago. Now, that design is then implemented over a 3 to 14-year build cycle. So it's also likely that if one of us went out and bought a new car today, it could be the best thinking a team of engineers had about what their customers might want 24 years ago, even though it's a brand new vehicle. Then we have verification and maintenance, just like we're used to in software teams. Agile takes this exact same cycle and loops it. Once we get to maintenance, we go back to requirements. Except on a software team, instead of waiting 10 years, we try to do it on the weekly. In fact, we try to do it even faster than once per week. We talk to our customer and say, what is it that's most important to you now? And then instead of delivering that 10 years later, or in a software project, maybe a large software project, 18 months later, or maybe 3 years later, we deliver it 7 days later and say, was that what you expected? Would you like us to make changes? As we've seen with software teams, that allows us to deliver extraordinary results very quickly at reduced cost, which is what attracts so many of us here to conferences like this, to share ideas on how we can implement these problem-solving methodologies even faster, even more faithfully, because we're delivering so much customer visible value that our customers are asking us again and again and again to use this software, or to use this process. So if a car is developed on a 10-year waterfall cycle, like old thought software teams would develop on an 18-month or 3-year cycle, and then now software works on a 7-day cycle or even tighter, what would happen if we put a car on a 7-day iterative cycle? What would be the constraints? Why isn't that happening already is another useful question. Let's use hardware from software teams as an example to try to explain this problem. This is the Redapt Cloud Rack. This is one way to do Agile IT well and quickly. The idea here is, instead of provisioning development environments, staging environments, load test environments, they're dynamically provisioned as needed. So you don't use power when you don't need to be using power. You're not paying for licenses when you don't need to be paying for licenses. And you're not paying for IT management when you're not taking advantage of those instances. And then it bursts to public cloud services for further on-demand storage and compute. This is Agile IT. This is not Agile IT. This is closer to how manufacturing happens today, and this is the computer used in the Apollo spacecraft missions from the 1960s in the United States. This computer system is special use. It's dedicated to solve one problem and one problem as well as it can, and to make a change requires changes in the power that's plumbed to the room, the personnel that runs the machine, retraining them on the new process, probably custom fabrication of hardware components, and potentially changes to the room or even the building it's in itself. The cost to change is expensive, which is the opposite of Agile. This is when it would be advantageous, in a way, to have that 10-year delivery cycle, because you get to force yourself to use this thing for 10 years and not have to buy another one or pay to make change. Existing auto manufacturing is very similar to this. This is a stamped steel die. This is a door being pressed. This is current. This picture was taken less than a month ago by Engadget, touring the Tesla manufacturing facility in Fremont, California. This door is stamped on this die, and that die, when you add in the materials, the machining hours, the maintenance of the machine that machined that die to stamp it, and the expertise to make that die, cost tens of millions of dollars. What that means is, using this method, which is the method that almost every single car any of us have touched in our entire lives has been made, if the engineer, the day after making this die, says, I've actually found a more valuable way to make this door, something that would be significantly more useful to my customer, they'd have to wait 10 years to make that change, because the cost of that die is too expensive. That's why that Honda Civic Hybrid, the front bumper, starts by looking clean and polished, and then 3 years later they add air vents. They changed one die. Because it was that expensive, they had to delay the change 3 years. Can you imagine the waste that would queue up, the refactoring opportunities that would queue up, if in our software teams we weren't able to do a code deploy for 3 years? Well, that was true not long ago. That's about the way software delivery was. Now, we've got it on the daily, if not even the minute, which enables us to meet our customer where they are now. We're able to rapidly iterate smartphone applications, even customer relationship management software and big business software, we're able to rapidly enhance to solve the customer's current problem with their feedback. But in manufacturing, we're still using stamped steel dies. Those dies are put into enormous press machines. These are 3 stories tall. This particular machine was moved from Detroit to Tesla's facility in California using 30 rail cars and more than 50 trucks. So the cost to even move this thing, whether you're using it or not, is enormous. The power draw is similar to some small towns. It requires unique training to use, and it's hundreds of millions of dollars. If tomorrow Tesla found a tool that did the job that this machine does better, they wouldn't want it, not from a business perspective. They've invested too much in this tool to change. It makes it difficult to be nimble when your tooling is very expensive. It does stamp out one door every 0.8 seconds. So there's a trade-off. There's a reason this is done. It's impossibly rapid. It has awesome power. It crushes these doors out of aluminum and steel panels using 3,000 horsepower equivalent across its 5 presses. Once you've decided on a given design, although your cost to make change has gone up, your ability to replicate that same price has gone dramatically low. Well, wouldn't the ideal case scenario then, doing a value stream mapping of this flow, be to have the same cost of productization, the same cost to repeat these assemblies, but reduce your cost to make change so that we could be agile and meet the customers where they are? In 2008, the Progressive Insurance Automotive XPrize was announced. It was a challenge to see if it were even possible to create 100 mile per gallon cars on again, the US cycle. So more than 150 miles per gallon imperial is the approximate conversion. It's not a direct conversion, but that's close. Is it even possible to build cars to over 100 miles per gallon US that met road legal specification? In 2008, what we had, the closest we had, were like bobsleds. They were like luges. One person, usually a small person, laid down in the car. And they looked towards their feet as they drove. And they would make a slow left turn on a closed course, often a temperature-controlled velodrome. The engine would fire 5 times, bringing their car to 25 miles an hour. They would then coast to 5 miles an hour, and then fire the engine 5 more times to get back up to 25 miles an hour. They achieved more than 100 miles per gallon. It wasn't on a cycle that was indicative of many of our commutes. It didn't hold any carpoolers, or any friends, or any storage, and it didn't have any crash safety, but at least we were making inroads on high innovation and high efficiency. The XPrize said, is it possible to make a car that people would want to drive that would achieve more than 100 miles per gallon on the EPA city and highway driving cycles? Those go over 70 miles per hour. That would hold 4 adults, that would have heat, defrost, air conditioning, that would emit less than 200 grams of CO2 per kilometer driven, that were safe. 136 cars entered from all over the world, representing the United Kingdom, Delta Motorsport, and Tata Motors, Tata based in India, but with their motorsports program headquartered in the United Kingdom, campaigned. In this larger blow-up diagram shows where some of the United States teams were located. There's a star over Denver, Colorado that says WikiSpeed. That was my garage. Many of these teams were well-known and respected universities, some of them with multi-million-dollar grants funding their initiative to build a 100-mile-per-gallon safe commuter car. Some of them were well-established companies, some of them with hundreds of millions of development dollars. And then there was my garage. I had no idea how I would compete with these teams, but I knew I actually couldn't sleep at night if I wasn't trying. It was a personal passion of mine. I began to blog everything that went well and everything that didn't go well as I was attempting to iterate an ultra-efficient, safe vehicle. Now this is a massive undertaking. Even being licensed to create a car for road legal sale is something that many of the teams are still struggling to accomplish. Luckily, one of my first jobs outside of college was on a 50-person Agile team developing the titling and registration system for one of the 50 states. And I had to learn the Code of Federal Regulations, which we printed it out as about that thick. Chapter 49, as it pertains to overland vehicles. And in that Chapter 49, it says everything required to build a road legal car and become a road legal automotive manufacturer. And I had to learn it for work. I was writing the rules engine for the titling and registration system. That would have cost millions of dollars in lawyer fees to register myself as an automotive manufacturer, but I was being paid to do it as part of my day job, so I registered myself as an automotive manufacturer. And I was prototyping these 2 ultra-low weight and as safe as I could chassis in my garage. Now, they weren't beautiful by a long shot. They weren't even that far along. But the XPrize was announced, and I said, well, I'm a software developer. I'll write an algorithm to simulate the EPA city and highway driving cycles, the fuel economy requirements. And I did, and then continued to put in all the cars that are currently sold, all their parameters, their weight, their rolling resistance, the type of tires they use, hundreds of parameters actually per vehicle, until I was able to get back the same fuel economy scores the EPA got. So I had indicative results. And it turned out I had just made test-driven development for automotive manufacturing from a fuel economy standpoint. And apparently that's not common. Apparently that's a little bit novel. So I'm blogging about what's going well and what's not going well. I'm asking really nerdy questions online, and I'm getting really nerdy answers back. It turns out a parking brake on most of the cars we drive now, actually all the cars we drive now, it has a rotor spinning and a brake pad that pushes on that rotor to slow down the car when you put on the parking brake. Well, that brake pad never leaves that rotor all the way. It floats on the rotor as we're driving, so there's some parasitic losses. There's some efficiency lost by just having a parking brake, even if it's not engaged. And I posted, I've looked at Ford parking brake systems, I've looked at Honda parking brake systems, I've looked at Toyota parking brake systems, I've looked at Mitsubishi parking brake systems, and they all do this. Does anyone know a simple, inexpensive to maintain, lightweight parking brake solution that we're not having these parasitic losses? Because when we're aiming for more than 100 miles per gallon, we really care about all of these small efficiency gains. And I would get comments back saying, oh, I'm so glad someone asked. I think about this all the time. We would get deep nerds when we ask nerdy questions. We went to the XPrize finals, passed every technical deliverable, and we had this ugly car. But it was absurdly efficient. and it met all safety regulations. And it had air conditioning, heat, defrost, and a stereo. It met all the minimums. It wasn't pretty yet. But we had this proof of concept that showed, yes, it was possible to build a 100-mile-per-gallon car. Now, if you remember, the XPrize put a $10 million prize to see is it possible to build a 100-mile-per-gallon car. Because they didn't know if it was possible. We built something that most people didn't know if it was even possible, and the version of the car that we brought to the XPrize was built in 3 months. Now, those of us who are working on Agile, Lean, and Scrum teams, most of us in software, are used to hearing these best-in-the-world metrics. Agile, Lean, Scrum software teams deliver value very quickly, much more quickly than other methods. So it's not entirely surprising that Team Wikispeed was able to make great strides with its methodology. Now, completely organically, 44 volunteers from 4 countries were members of Team Wikispeed by the time we attended the Michigan International Speedway events for the Progressive Insurance Automotive XPrize. 16 of us flew out to MIS, Michigan International Speedway, to campaign the car. Not all 16 of us are in the picture, but most of us are. We took time off work unpaid. We paid to fly ourselves in. We paid to stay in a motel. And we tried to change the world. And in a small way, we did. We showed all the large automotive manufacturers, and we showed each other that it is possible to build 100-mile-per-gallon cars that meet road legal safety specifications. The gentleman in blue in the center is Al Unser Jr. He's 2-time Indianapolis 500 champion. He was a hired driver of a team campaigning against us. He was in the pits next to us, and he saw something he thought was neat. While other teams were checking their tire pressure, while other teams were topping off their fluids, we were able to strip our car down to the chassis and reconfigure the car in an alternate configuration. We were continually iterating our car even at the racetrack. He hadn't seen this before, and ended up spending a fair amount of time with our team. Here we are in a swarm from Extreme Programming. I'll get to talk a little bit more about that in a minute. And we're changing all the modules of the car. The car splits apart and reconfigures. Ultimately, we tied for 10th in the mainstream class. This logo was when we became a finalist. It has these green laurels on the side. That was an enormous positive event for our volunteer team. We gave each other jumping high fives all over the place when we got this logo, when we became a finalist. But we didn't win. We didn't get the $10 million prize purse. It was ultimately split across 3 classes. We tied for 10th in the mainstream class. What that did mean is we came in ahead of more than 100 other cars. What that did mean is some of those teams were some well-known brands and universities like MIT and Tesla Motors. We outlasted both of those teams. And we were then in Popular Science and Popular Mechanics and Wired Magazine and the National Geographic Channel. We had international press for achieving this feat, even though 9 teams ultimately did even better than us because we tied for 10th. Our team grew. We were now more than 50 team members. And we said, let's see if any part of our car is applicable to the market. Makes sense for people who are looking for cars now, something ultra efficient. Let's see if we can make it desirable. Take it from a functional proof of concept to something maybe some people would want to own. We were using Scrum the entire time. Now, at this conference, we're all going to get to learn a whole lot more about Scrum and what makes it work well. Scrum at a very high level is team management. So Agile is rapid iterative delivery. Scrum is what's the least you need to do to responsibly have a highly effective Agile team. So Scrum can be applied to the company. Scrum can be applied to a portfolio of teams. Scrum by itself is a team methodology where you have a group of people, typically software developers, but as you can see, it obviously doesn't have to be, working very quickly to create customer visible value. And we knew we were a Scrum team because we had the roles, artifacts, and ceremonies of Scrum. They served us with an enormous amount of value. We have a product owner with a clear vision of the final version of each part of the car we're working on. who's able to rapidly say that's on track, that's not on track, and they're embedded in the team. We have a Scrum Master who's always assessing the team to say, are we using process to the highest available effect? And then we have the team. Now, when we started out, we didn't know how to build a 100-mile-per-gallon car. No one did. But what we knew is, to build a car, you need to do these types of tasks. And our team could do those. We could do TIG welding. We could do composite layup. We could do fuel economy and emissions testing. We could do the tasks. So by continually marching to the product owner's vision, we were gradually able to achieve what was seemingly impossible. Not because we knew our team could achieve the final result, but because we knew our team could achieve each task in our backlog. Then we absolutely replaced every meeting any of us had, nights and weekends, with just the 2 meetings from Scrum. Our daily stand-up, but in our case it's a weekly stand-up because we're in every time zone all over the world, and we're doing this nights and weekends. So it's, what did I do last week? What am I doing next week? Do I have any blocking issues? And then our demos. And our demos we typically film and then share with the team. Some of them are on YouTube. Scrum lets us reduce time spent doing anything but creative problem solving because we have all this time back. We're doing the very minimum required to have a highly functional, fast-moving, agile team. We then, 6 months after the XPrize, made a structural composite aeroshell that looked much better. We were invited to the North American International Auto Show, which in terms of attendance is the largest auto show in the world. Now, you saw our orange car body. We were flattered that any car show wanted to have us anywhere near them. 750,000 attendees came to this show. 5,000 members of the credentialed press representing more than 60 countries came to this show. We figured we'd be put in a back corner of the basement if we were even allowed in. We rushed to make a structural composite body. We put out bids to say how much would it cost for us to have a structural composite body. We absolutely wanted to have a carbon fiber body, but carbon fiber is extremely expensive to work with. It's reserved for aerospace and the most expensive supercars. The least expensive car that you can currently purchase with an all-carbon fiber body, aside from the WikiSpeed car, is the Ferrari 458 Italia. That car starts at it's about $230,000 United States. We put out bids. The least expensive bid we received back for making a body for our car was $36,000, and it would take 3 months. Now, that bid was from someone that I was personal friends with, that I'd met at composite school. And he wasn't going to charge us for anything except the materials and the parts of the labor he had to contract out. He wasn't going to charge us for his time, which is why that bid was so much cheaper than all the others. We applied Agile methodology, and again, just like most of us on Agile, Lean, and Scrum teams are used to hearing best in success metrics, we found a way to make a structural carbon fiber body for $800 US in 3 days. That had never happened before. Thanks, guys. You're awesome. So we have this ultra-efficient set of mechanicals, and now we have the ability to make whatever shape, size, color, picture, car body we want out of the most light, rigid, and energy-absorptive material man knows about right now. So we're set up to do awesome stuff. So what did we decide to do? We took it to the North American International Auto Show, and they put us on the main floor between Ford and Chevrolet. We were panicked. We didn't know how that would turn out. We were excited, but we're working in storage units and people's residential garages, and now we're next to some of the largest automotive manufacturers in the world. The next morning after our press conference, we had press in every UN language: Russian, Japanese, Estonian, American English, European English, every UN language. And my favorite quote is blown up at the top. It's from Automotive News. WikiSpeed is a reminder of the true spirit of the Detroit Auto Show. Some companies are still building mind-boggling, revolutionary cars because they can. We were thrilled. We were in the New York Times online. We were linked to from Forbes Billionaire Club. For a group of all volunteers working nights and weekends, we were ecstatic that we've been able to make a dent and show that you can actually change cars really fast. You can actually improve efficiency and performance very quickly. Automobile magazine is one of the more conservative of the major automotive publications. They then did a 3-page article on us. They called it Above Average Joe's Can-Do Car Company. They put it in the same issue as Mercedes-AMG Gullwing sports car. And what a juxtaposition that is. Then the Discovery Channel Canada came to visit our shop in Seattle, Washington. And here's me driving the car past the camera. That should air just in the next couple weeks here and be online on discoverychannelcanada.com. Here's the Discovery Channel actually about to hop in and go for a ride. Then we've opened 2 composites facilities since, one in Germantown, Maryland, and one in Everett, Washington, where Boeing is, the aircraft manufacturer. And now we've decided, since we have this ultra-efficient vehicle with this very safe chassis, and we're able to make bodies in any shape we like, we thought we'd make something kind of cool looking. And we have this convertible city car in progress. That's Rob Moorbacher of Moore Composites. He's drawn our last 2 cars and many other cars that we hope to make soon, and he's directly overseeing the build of this production mold, where we can make glossy, shiny carbon fiber cars in this convertible city car configuration. That car, this is a rendering,